Section 2, we're going to talk about more about data and types of data, and then ways that we can collect samples and how we might see some variation in our data and sampling. All right, so data in general can be put into two categories. The first is qualitative data, and the second is quantitative data. And you may be able to tell just from the names here what kinds of things we may be dealing with. Starting with quantitative, that shares a root word or shares a root with the word quantity. So you may already be thinking, well, that probably has to do with numbers, and it does. It's either counts of things or measures of things where we are receiving our data in numerical form. Qualitative data, on the other hand, shares a root with quality, and so these are things where typically we're just providing a label or a category for this data. So some examples would be for qualitative data, perhaps hair color, or your favorite ice cream, or what you're going to major in college, things like that. Sometimes this data is also referred to as categorical data because we can put these various things into different categories, and so that kind of makes sense. Quantitative data is where we are actually getting numbers. So typically these are the result of either counts or measurements. So things like income, weight, your age, how many siblings you have, things like that. Those are quantities that we can either count or measure. Inside of quantitative data, there's two subcategories that we need to talk about, and that would be discrete and continuous. So discrete data is where there are only a limited number of possibilities. Okay, so typically discrete data is the result of counting. Okay, so if I asked you how many siblings you have, 3.7 is not a legitimate answer, right? We are limited on the number of values that these answers could take on, right? You either have 0, or you have 1, or you have 2. You don't have fraction or decimal answers to questions regarding discrete data. Continuous data, on the other hand, is on a continuous scale. So however accurately we can measure something, that's how many decimal places, for example, we could include in our data. So these are usually measurements, lengths, weights, times. So if we have a scale that measures down to the millionth of a gram, then we could have data that was that exact. On the other hand, we probably don't. So but it's totally fine to have 21.67 grams, right? As long as our measuring devices are that accurate, then we can include numbers between the whole numbers. So measurements typically provide continuous data. Counts typically provide discrete data. So just to give you a little more in-depth example here, as a discrete case, perhaps you are interested in the number of books that students carry around in their backpacks. So you sample 5 students, and 2 of them are carrying 3, 1 of them is carrying 4, 1 student's carrying 2, 1 student's carrying 1. So the number of books that you have give you discrete values, 3, 4, 2, 1, etc. On the other hand, maybe you want to know how much do people's backpacks weigh. So this would be a different type of data, right? We wouldn't be counting books, we'd be measuring weights. So here we get 6.2, 7, 6.8, 9.1, etc. Okay, we see that it's totally fine now to have decimal answers because weight is a continuous scale measurement. On the other hand, when we have qualitative data, like for example here we're talking about 2 different colleges, and we're just basically surveying how many people are full-time, how many people are part-time. Well, full-time is not a numerical value, right? Part-time is not a numerical value. So quite often with qualitative data like this, we are going to be able to deal with proportions or percents pretty reliably. So tables like this are useful because here we have 2 different size colleges, right? We can see that De Anza College is much bigger than Foothill College. And so if all you had were the raw numbers, part-time students versus full-time students, you might, jump to the wrong conclusion here. So, for example, if we just looked at part-time students, we see that De Anza College has 13,000 plus, and Foothill College only has 10,000. So we might think that a greater, because there's a greater number at De Anza, that that means that the percentages are also higher at De Anza, but we can see here in this table that that in fact it's not. So percents and proportions are really helpful when you're dealing with populations that have different sizes, so that you can really sort through what's going on in the population more reliably. Another good way of looking at data is in graph form. Okay, here we have a pie chart, part-time data, part-time students, full-time students at both colleges, and this gives us a good visual of how the student breakdown works. Another way we could do it is in a bar graph. Here we see part-time and full-time in just a slightly different way. It gives us just a different visualization. And while we're talking about percentages and proportions, it's important that we are really careful with our percentages, right? Typically we know that if you've counted everything, if you're dealing with all of it, then that's 100%. So you shouldn't really have more than 100%. So some instances though, like here we have full-time students, students who intend to transfer, and students under the age of 25. Well, those three things can all happen at the same time, right? You could have a full-time student under the age of 25 who intends to transfer, and so these percentages are not going to add up to 100, right? Because they're not mutually exclusive. If you had students under age 25 and students over age 25 and you added those two together, that should give you 100%. But here we have three different questions basically that are being asked, and so if we add these percentages up, we get something greater than 100%. So this doesn't mean that an error occurred, right? It doesn't mean, well, I would say there probably is an error, but the only error is that they tried to add these percentages up. Okay, the 40.9% is probably an accurate number. The 48.6 is an accurate number. The problem is not with the data itself. The problem is you need to know when it's okay to add your percentages up and when it's not. Okay, and in this case, because you're dealing with three completely different questions, it doesn't make sense to add these up. So just kind of beware of issues like that when it comes to percents. Should never really see a percentage greater than 100. This is another type of bar graph. It's specifically called a Pareto chart. We use Pareto charts when our data is categorical or qualitative. So notice here at the bottom our categories are Asian, white, Hispanic, etc. These are not numerical things, these are categorical things. So Pareto charts are useful for that, and specifically in Pareto charts you'll see that we always have our data organized so that the largest percent, the largest bar is first, and then the bars go in descending order after that. So that's just called a Pareto chart. All right, I want to talk a little bit more about sampling. Ultimately, we talked in section 1 that what we're really shooting for is a representative sample. We want a sample that shows us the characteristics of the population as much as possible. So the best way to do that is to introduce randomization to our sampling method. Okay, we want to try to take our own personal bias out of it and try to do things in a way that's truly random. So the best way to do that is with a simple random sample. So the difference between random and simple random is this. Okay, in a random sample, every person or every member of the population has an equal chance of being selected. Okay, so maybe everybody has a 50-50 chance. All right, but a simple random sample goes a little further and says that say you have decided on a sample size, right? Say you're going to sample 10 people or 10 items. Okay, a simple random sample is one where every single possible combination of 10 items or 10 people is equally likely. Okay, so I'm going to give you a little bit better visualization of that. In order for a sample to be simple random, you basically have to be choosing one item at a time from the entire population. All right, a couple ways you could do that. You could draw names out of a hat. You could use a random number generator. Lots of different ways you could do it, but here's the visualization I was talking about. So say we have these 8 things that are labeled A through H. A couple ways that I could sample. Okay, let's start by saying, all right, what if I take each of these and I put them into a group? Okay, so we got group 1, group 2, and I just assigned, in this case, A through D to group 1, E through H to group 2, and now I'm going to flip a coin, and if it's heads, I'm going to take group 1, if it's tails, I'm going to take group 2, and we'll just say it came up tails. So here's my sample. Okay, my sample has 4 items in it, and this has given me a random sample. However, it is not a simple random sample. Okay, in order to get a simple random sample, I just need to have all of my data values just sort of there, and I want to use some random method to select individuals. Okay, so I'm going to use a number generator, and it's going to give me numbers 1 through 8, and so I'm going to get these 4 values completely independent of one another. Okay, this on the right would be a simple random sample, and the reason is if we go back and look at the left side sample for a second, the group 1, group 2 samples, notice that there's no way, with the way I've split them up, that I could get a sample that includes A, B, E, and F. Okay, that sample is not possible. So that means that that first sampling method on the left is not simple random, because every single possible combination of 4 items needs to be equally likely. Over on the right, okay, I used a random method to select individuals, so every single sample of size 4 was possible. Okay, this happened to be the one that I got, but it's equally likely that I could have gotten, say A, B, C, D, or A, D, G, F, or any possible combination of 4. Okay, so on the left we have a random sample. It is random. Everybody had a 50-50 chance, right? A 0.5 probability of being selected because I just flipped a coin. If it came up heads, then the first group would win. Came up tails, the second group would win. But everybody had a 0.5 probability because that's the probability of flipping a coin and getting either heads or tails. Over here, everybody also had, well, let's just say this. Everybody had an equal probability, but more importantly, every possible sample of size 4 was equally likely, and so that gives me a simple random sample. Okay, some other methods to talk about. Stratified and cluster are similar, so I'll kind of talk about them together. In stratified, we have stratified and cluster both. We have people that are already split up into groups, and this may happen maybe geographically, like maybe you've got people in different zip codes. Okay, so you want to sample some people from the 30144 zip code and some people from the 30152 zip code, and so on and so forth, so that people are already in groups. And then for stratified, what you want to do is you want to take some people from every one of those groups. Maybe a more tangible example would be, we have people grouped by class at North Cobb Christian, right? We have 9th graders, 10th graders, 11th graders, 12th graders. So say you want to take some from each grade level to make your sample. Okay, that would be stratified sampling. Okay, on the other hand, cluster is where you have people in groups already, but instead of taking some from every group, you just take all of one group, or maybe you take all of a couple groups. Okay, but in cluster sampling, you're making sure that you get all of a particular group. Another type is systematic. This is where you take every nth item based on some starting point that is randomly selected. So this is the kind of thing that you might see in like a manufacturing setting. You're doing quality control on the items that are coming off your assembly line. So, you're going to randomly pick the first one, and then after that, you're going to sample every 10th item to make sure that your quality is up to par. Okay, so that would be systematic. You have a system in place where you're taking every nth item. So some non-random methods would be, oh, by the way, I should point out, the stratified and cluster are still technically random if you are choosing the individuals or choosing the clusters in a random way. Okay, I didn't say that specifically, and I should have. All right, so non-random methods. These are ways that we should probably try to avoid if possible. The first is convenience sampling. That's just where maybe you're trying to take a sample of the senior class, so you just count the first 10 seniors that you see walking into the gym one day. Okay, that's that's an easy way to collect data, but it's not necessarily random, and so we want to try to introduce that randomness into our data to avoid any sort of bias. Okay, so convenience sampling is just getting data the easy way. Self-selected sampling, these are things like voluntary online polls or something. If you see a Twitter poll or an Instagram poll or something like that, those are self-selected samples. Basically, people are choosing whether or not to participate, and we typically try to avoid those because quite often the only people that respond to those types of surveys are ones that have, passionate feelings about them, right? If it's a political thing or if it's whatever it may be. People typically only respond to those if they have some sort of vested interest or some significant interest in that. In example 1.1, what I want you guys to do is pause the video here after I've given you a chance to see all of these choices and see if you can determine the type of sampling done. So here's A and B, so maybe pause and see if you can check those out, and then next I'll show you C through E. Okay, so hopefully you've had a chance to look at all the choices, and so in A we have a sample of 100 undergraduates, and we are organizing them by their grade level, freshman, sophomore, junior, senior, and then we're selecting 25 students from each grade level. So that would be an example of stratified sampling. Okay, we're taking some from each category. For B, random number generator used to select a student from the alphabetical listing, and then starting with that student, every 50th is chosen, and that would be an example of systematic sampling. For part C, completely random method. Each undergraduate has the same probability of being chosen at any stage of the sampling process. That would be a simple random sample. The freshman, sophomore, junior, and senior years are numbered 1, 2, 3, 4 respectively. Random number generator picks 2 of those, and then we sample all the students in each of those categories. That would be cluster sampling. And then we have an administrative assistant who's asked to stand in front of the library one Wednesday to ask the first 100 students he encounters. That would be convenience sampling. All right, the idea of replacement quickly is just whether or not we are introducing the possibility that a person could be chosen more than once, or an item could be chosen more than once. So with replacement sampling, we take a sample, we choose an item, we record the value of the data, and then we put it back in the pool, and then there's a chance that we could pick that same thing again. Usually we sample without replacement for practicality, but if our population is really, really big, then it doesn't actually matter whether we use with or without. Most of the calculations that we do consider replacement, and the calculations are usually a lot easier if we have with replacement. So usually we're gonna assume that we're sampling with replacement, even though in practice sometimes if we have a really large population we might not. But it's okay because the really large population doesn't change the probability values very much. couple types of errors. Sampling errors are caused by poor sampling methods usually. We're going to do our best when collecting samples to avoid sampling errors. Non-sampling errors are everything that can happen after that. So maybe we make a mistake with a calculation, or maybe as we collected our data, our scale was screwed up or whatever. That's not necessarily a problem in how we collected our or how we chose our sample. Maybe there's an error in how we collected our data or a calculation we did afterward. So with critical thinking, I'm not going to read all of these, but one of the most important things that I can impart to you is that anytime you're dealing with statistics, you really need to be able to think critically. So these are all things that you can read in the textbook. I'm not going to go through each of these, but anytime you encounter a statistic in life, okay, you need to think about, where did this data come from? Who created this sample? Who paid for it? What are they trying to prove? And what could be some issues with the statistics that you're seeing? Critical thinking is a really important part of what we do. All right, variation is just the idea that you take two samples from the same population, you're probably not going to get numbers that are exactly the same. Okay, so if you were to want to maybe find the mean height of students at NCCS in the upper school, and you take two samples of 20, it's very likely that your averages for those two samples will be somewhat different. Okay, and that's fine. Doesn't mean you screwed up, doesn't mean you did something wrong. Sample size will affect the variability to a good degree. So if you're really worried about it, then you can increase your sample size. So if you took samples of 20 students and you found their mean height, there could be a good bit of variation there. But if you took samples of 50 students and found the mean height, those two samples would probably have means that are a lot closer together. So as long as you selected your sample in a random way, then you should be fine. This last statement here says sample size won't fix sample bias. Well, if you're not using a good random technique for collecting your data, that's not going to fix the variation problem. All right, so again, your suggested problems are from the homework section, as you can see here. So any questions that you might have about this homework, we can discuss during our office hours time coming up. All right, let me know if you have any questions, and thank you very much.